All right, let's get into stars. So the objectives of this subunit are going to be to explain why some constellations are only visible during certain seasons and to distinguish between absolute magnitude and apparent magnitude of stars. This is talking about brightness. All right, so constellations, what are they? They are groupings of stars that ancient people thought looked like something. So Ursa Minor, Ursa Major, Orion's Belt, all of those like old school constellations that you think about, that was just people looking up in the sky, connecting the dots, and then kind of thinking that they looked like some sort of object. Our modern constellations are going to be things like Big Dipper, Little Dipper, the Big Dipper correlates with our ancient one, Major, and the Little Dipper correlates with Ursa Minor. The funny thing about stars, however, is whatever like symbol or sign you think you are, Virgo, Capricorn, Pisces, all of that, that changes every 20,000 years. So 20,000 years ago, you may have been a Virgo if you're a Cancer, something like that. So constellations and like getting anything out of it is not real. Sorry to burst your bubble. So here's just Ursa Major. Kind of looks like a bear. Not really, but kind of. And it's going to also be the Big Dipper there. So we've got Polaris here at the end. And then we've got the Little Dipper right here, and this is Ursa Minor. And so this doesn't really look like a bear at all either. But sorry, here's the North Star on the Little Dipper. Excuse me, it's on the little one. And generally they kind of connect. They're really close to each other. They have these pointer stars that point towards the North Star, and that's how you're kind of able to navigate throughout the night with just using the stars. It's not just the North Star. The North Star is not always true north, so you have to be able to use these pointer stars to use geometry to navigate where you are. So we've got things called circumpolar constellations. So circumpolar constellations are basically, especially in the northern hemisphere where we live, they're constellations that swirl around Polaris as Earth rotates, and as Earth rotates and tilts with the seasons, they're going to change around the sky. So it's going to look like the constellations are in a different part of the sky than they were in the summer than in the winter, that type of thing. So Orion's Belt is a good example of that. It's only available during certain times of the year. I believe it's the summer. I could be wrong, but it's not visible during the other seasons. So it's going to be visible in the southern hemisphere. And that's due to parallax. We'll get into parallax a little bit further on, but mostly due to just the Earth's tilt. Like I said, it's kind of the same reason why we have seasons. The Earth is tilted, so if it's like tilted like this in the summer around its orbit around the sun, and it goes around here, it's going to be tilted like this. So you're going to be seeing these constellations, say like right here in the summer, but as it tilts and rotates around the sun, you may be seeing them over here. Excuse me. So that's just why that happens. It's called a parallax. I think I get into parallax. Yeah, I do. Okay. So, absolute magnitude and apparent magnitude, this is one of our objectives. This is just like brightness of a star. And the apparent magnitude is what you see from Earth, essentially. It's from where we're looking, our perspective. And it's just tells us how bright the star appears to be from Earth. So it's our apparent magnitude. The sun is apparently very, very bright from where we are, but it's really not that hot or bright of a star in comparison to other stars in the galaxy. So absolute magnitude is how much light it actually gives off. And how do we find that out? Well, we have telescopes that can look at stars, and then we also have things called spectrographs or spectrograms, and these are like things in science where we can monitor the wavelength of a certain beam of light, and that wavelength tells us all sorts of things about energy, and so we put this spectrograph inside of a telescope. We call it a spectroscope, and that's going to tell us, as we're looking through a telescope, what light wavelengths are coming through to us, so we can tell just like how hot that star is and how bright it is, what kind of light is being given off by that star. And so here's just a spectroscope and how it works. So we get a star. That star is going to shoot light out. The spectroscope kind of creates a little bit of a prism inside of that telescope. The prism is going to separate light. And so whatever light comes through and like hits the spectrograph, we we get that as a number in wavelength. So it says recorded on a photographic plate. That's just a spectrograph. And it goes from like hottest, pretty much most energy, but we'll say hottest to coldest, starting from purple, blue, green, all the way up to red and orange. Red and orange are going to have the least amount of energy associated with it, so they're going to be cooler stars. So let's get to measurement in space. This is that parallax we were talking about, why we see constellations in different times of the year in different areas of the sky. So I just made a bunch of hand motions that probably don't make any sense, but that's all right. The parallax is the change in the angle of visibility of constellations from Earth from season to season due to the tilt of the Earth's axis. So essentially, in layman's terms, the Earth tilts, it rotates around the sun, and with that tilt and the change of seasons, we see these constellations at different areas in the night sky. So, those constellations don't move. They stay where they are, and they're really, really far away. What's moving is us in our perspective. So here, we may see a constellation up over in that region, and over here in the winter, we may see the constellation over in that region. So what we do is we use geometry to configure the lines of sight, of visibility from those constellations by season to season to actually be able to measure the distance of how far away those stars are. And so it's really actually simple geometry that we can use. People have been doing this for a long time. And they use, nowadays, with modern technology, we use a light year to kind of measure distance. And a light year is just how far light can travel in 1 year. And light is the fastest known thing. If you go faster than light, it's speculated, Einstein speculated that if you can go faster than light, you can break the space-time barrier, so you can go back in time. That's the whole idea of time travel, is going so fast that you're going faster than light and able to manipulate space and time however you please. So we don't have any technologies that are even close to light speed. So just think about that for a second. A light year, we've measured in kilometers, is 9,460,528,404,846 kilometers. And in miles, a light year is 5,878,499,812,499 miles. So that's how far light can go in 1 year. It's amazingly fast. It's about 300,000 kilometers per second. So, think about like how you go 80 miles an hour in the car. These things are going 300,000 kilometers per second. That's extremely, extremely fast. And all this tells us is that space is huge, huge. So when people talk about how there are planets that we may be able to habitate in other solar systems, these planets are light years away. They're not just one light year away. They're hundreds, thousands of light years away. So to be able to get a human population from Earth to one of those planets is going to take many, many, many generations, like probably like 6 generations or so, 6+ generations. It's going to take a long time to get to those places. So yes, they are habitable zones, but we can't really get to them. So especially with current technology. So we really need to make sure that we take care of this planet because we don't have anywhere to go. There may be places that look like they're nice, but we can't get to them. So here's just showing you how enormously large the universe is. Here's Earth right here. We're in our solar system. Here's the sun. Here's all of our planets in this solar system. And we've got the Kuiper Belt around here. And then here's our interstellar neighborhood, which is just other solar systems in our galaxy. So here we are. There's all these solar systems in our own galaxy. So think about, our sun, Mercury, Venus, Earth, Mars, Saturn, Jupiter, all those are in one solar system. Here are about 20 solar systems in our interstellar neighborhood. Here's the Milky Way galaxy, which is full of interstellar neighborhoods. So each one of these little dots is an interstellar neighborhood. Here's our local galactic group, which is a bunch, just imagine more Milky Way galaxies. Here's ours. Here's Andromeda. We're on a collision course with that one. There's a bunch of other little galaxies right in there. Here's the Virgo supercluster, which is just a bunch of local galaxies and other galaxies put together. So, it's just starting to get larger and larger. Here are local superclusters, which are superclusters that are relatively close. They're still light years away. So, here's our Virgo supercluster. Look at all these other superclusters with all of their own galaxies and all of their own interstellar neighborhoods. And then here's the observable universe. And all those little dots are going to be superclusters. So, just to put it into perspective, the universe is amazingly large. It's so large, no one can quantify it. No one has any ability to think about it in their brain because it's too big. Okay, so properties of stars. What are some properties we look for? Well, we look for how much heat they give off. That's a big one. So we can tell this by using that spectroscope. And a spectroscope is just a device put into a telescope that acts like a prism. It separates light that is being observed, and each light has its own specific wavelength, which we can then correlate to heat. So the cooler colors, and I'm talking cooler as in like in the color spectrum. So blue, violet, green, those are cool colors, but those correlate to the hottest stars because that wavelength correlates to the most energy. So warmer colors like yellow, orange, and red are actually going to be the less hot stars. So if you see cool colors, just think of the inverse, the exact opposite of that. Cool colors, hot stars; warm colors, cold stars. Well, comparatively cold stars. And then here's how the spectroscope works. So when we look at stars, we want to tell like what kind of elements are in there. Most of the time it's going to be hydrogen and helium, but about 3% are going to be constituents of oxygen, neon, iron, magnesium, silica, some other small elements. This is going to be a really small percentage. Most of it's going to be this. But you see these lines here. These lines are the lines that generally are hit in the wavelength of these elements, because every element gives off its own wavelength in radioactivity. So we know that this is hydrogen and helium's typical spectroscopic wavelength here. So these are the hits right here. So now let's look at stars' spectroscopic wavelengths and see if we can find, right in the middle of the blues there, a bunch of hits there. We're going to see that those are helium and hydrogen mostly. Here's a good one right between green and yellow. So let's check it out. So here's one right between green and yellow. Right there, that's helium again. So we look at this star here. It's kind of a blue star, so it's probably extremely hot. So we look on here. We can tell that, hey, yeah, it's getting hits of whatever this element is. It's getting hits of helium. You can see this line correlates with this line. We get one right in there. That's probably going to be whatever this element is. And then look right here between the orange and the red. Boom, hydrogen, helium. So that's how we do it. That's how we figure out like what is in the stars, because we can't actually go there. We just look at the light. This isn't 100% accurate all of the time because there are elements that we're constantly finding. And since those stars are so far away, we don't really know how they're interacting with gravity, other elements. There could be just random new elements being given off because there's so much energy and so much pressure in stars. We just really know what's in our local supercluster. So that's going to be it. If you have any questions, comments, or concerns, go ahead and let me know. I know this is kind of difficult to comprehend because it's a lot of information all at once, but that's what I'm here for. So if you have any questions, let me know, and otherwise have a wonderful week.